Hello everyone, welcome to Mayur Programming Club. Today we will be solving another daily LeetCode problem, and the problem's name is strange printer. So the problem statement goes like this. There is a strange printer with the following two special properties, and the properties are that the printer can only print a sequence of the same character at a time. Okay, and each turn printer can print new characters starting and ending at any place and will cover original existing characters. Okay, so what the problem statement is saying here is, if there are some characters already printed by the printer, first of all the printer cannot print something like this a and b together. Okay, the condition being that the printer can only print a sequence of same characters each time. Okay, so it should be either a or bb. Okay, so if you want to print a substring of length 2, okay, and let's say there are some characters already present, let's say 3 a's were present there, and or let's say 4 a's, and you want to print something like this a b b a. Okay, then what you will do, you will place the printer starting point here and have a length of 2 and place 2 b's. Okay, so these 2 b's will cover these 2 a's or replace these 2 a's, so these are gone and the new string becomes a b b a. Okay, I hope you are able to understand what this is meaning, that each turn the printer can print characters starting and ending at a place and will cover the original characters. Okay, so now moving further, uh, before thinking of an approach to solve this particular one, let's have a quick look at the constraints. So according to the constraints, the length of the string will be of order 100, and the string will consist of lowercase English letters. Okay, so these are the two constraints. So let's think of a brute force way to solve this particular problem. The very first approach that came into my mind was a brute force approach. And in a brute force approach, what you can do is you can try out all possible combinations that can be there. Okay, so if you are trying to match a particular character in the given string, let's say the given string is a b b. Okay, and you are trying to match this character at this particular one, let's say you have matched the previous characters, it is already done. So this is the new string that you are generating. Okay, new string. So if you are trying to match this particular one, then starting from here, what is the length of the substring that you might want to have? Okay, so at each index O of n choices will be there, order of n choices, because if the string is of size n, then you can at max print n choice order of n length substring starting from a particular index. So each index order of n choices in terms of length of the substring starting from this particular index at which you are at currently and trying to form the string that you might wanna take. Okay, so and if the string is of length n, so this order of n will be repeated n times and multiplied. So the overall number of operations required will be of order n raised to power n. Okay, and as mentioned in the constraints, the n here is 100, so it will be very large, 100 raised to power 100. Okay, number of operations. So these operations will be definitely larger than the operation limit. So there is one operation limit of order of 10 raised to power 8 operations in most of the online judges. So if the number of operations exceeds this limit required by your program, then you will get a time limit exceeded and your solution will not be getting accepted. Okay, so that's why you will be needing to optimize your brute force approach. Okay, brute force approach will not be working here. Okay, and if you might think that, okay, why should we apply brute force approach, we can use a greedy approach. But you know, greedy choosing a locally optimal solution always will not always lead you to the globally optimal solution, or the you can say, if you are choosing optimal decision for a sub problem, then it will not result in always result into the entire problem being solved optimally. That's why greedy won't work. So we need to make a couple of observations for this particular problem. And what are those problems observations? The first observation is there are overlapping sub problems in the given problem. So what are overlapping sub problems? It's nothing but if there are two combinations, let's say combination 1 and 2, okay, so in those combinations some part of those combinations overlap, okay, like you see that A is repeated once, B is repeated twice, C is repeated thrice, and G is repeated 4 times, okay. And there is one another combination. These are just choices that you have made, okay. This was the character that you wanting to print, and this was the length of that character, okay. So in a way you can imagine it like that. So then first of all you printed something like this, G 7 times, then you replaced G with C 3 times, okay. Then you achieved the same result, but you know this particular two combinations were having this much part in common. So overlapping subproblems were leading to extra work due to recomputations for these two subproblems, okay, of different combinations. So in order to avoid that, and it should be avoided, we should be storing the results of the subproblem, okay. So storing results of subproblem. Okay, so results are nothing but the minimum terms needed for solving this particular subproblem. Okay, and the second observation is optimal substructure. So what is this property? You can see that if you know the optimal number of turns needed, uh, okay. So what you have to tell is you will be given a string. Sorry if I don't covered this part. So you will be given a string and you have to return the minimum number of turns to print it, okay, given these two properties of the printer that you are having. So printer will be taking turns or iterations one after the other, okay. So you need to tell what will be the number of turns, okay. So in order uh, to get the number of turns needed by the printer to solve this whole bigger problem, if you know what will be the optimal number of turns needed for this smaller subproblem, then it can be used to get the optimal decision for this part also, okay. So this leads to the second observation, which is that solution of smaller subproblems in this particular problem can be used to form the solution of bigger subproblem, okay. And this property is called optimal substructure. And if you are hearing these two properties of a particular problem for the very first time, then what I will do is I will provide link of articles explaining these two properties in depth, and you can definitely check those links out in the description box of the video. And now moving further, once these two properties are satisfied by a particular problem, then that problems becomes a valid candidate to be applied dynamic programming on, okay. And even if you are hearing the dynamic programming word for the very first time, or you do not know anything about this technique, it's just optimization over brute force. And link of this particular techniques article will also be provided in the description box, so you should definitely check it out if you are not familiar with it. So what it does essentially is it stores the subproblem results, as we already talked about in this particular section, that due to overlapping subproblems some extra work is done because those problems results needed to be computed again and again. So why not just store the results of those subproblems, basically all the subproblems, and if they occur again, then you will just be returning from your memory instead of doing the computations again and again, okay. So in a way you can say that to save some time complexity you are trading some space, okay. So you will be storing the subproblem results, and in that way extra work will be avoided whenever those subproblems again occur in some another combination. Okay, and the second thing is that bigger subproblem solutions will be formed from smaller subproblem solutions. So this is what dynamic programming is in nutshell. And if you want to have an in-depth understanding of it, then please check the link that I have provided in the description box of an article regarding dynamic programming. Okay, so assuming that you have now familiarized yourself with those two properties, what those two properties are: overlapping subproblems and or optimal substructure and this dynamic programming technique, uh, then we are good to go and to see how we will be solving or applying dynamic programming in this particular problem and solving it eventually. Okay, so what we will be doing here is, firstly, for each of the, if we have decided to apply dynamic programming on a certain problem, then you need to know what is done, what are the variables that are defining your current state. Okay, so variables defining your current state. Okay, so here you will see that there are two variables that, or these are called state variables, that define your current state. The first one is at the index at which you are at. Okay, so if you are at a particular index and let's say the character given is, the string given is, let's take some different color, a and then b, and you are at this particular index. Okay, so starting from this particular index, what is the length of the substring that you will be wanting your printer to print? Okay, so you might be wanting to print the entire way, or you just want to print a single character or double characters. Okay, it's totally up to you. So these, the index and the length of the substring you want to print, two variables will be determining your current state. Okay, current state is like in the process of decision making, at which instance or the state you are at. Okay, so that is what state is here. Okay, so two state variables that translates into a two-dimensional dynamic programming structure needed to be used to store the results of sub problems. Okay, so that's why 2D DP will be there. So I have named that structure and we have used an integer array for that, since we have to return the number of minimum number of turns needed. So a integer array will be good to use, and I have named it the turns needed. Okay, and what it represent is, it represents starting from which index and ending from which index you want to place your current substring. Okay, and you might be thinking you are not using the second state variable, which is length. So to get this end index, we will be using this formula: start index plus length minus 1, and this length is nothing but the second state variable and start index is the first state variable. Okay, so I hope till now it's clear to you. And then once you have decided the number of state variables that will be needed, and then you have decided the dimensions of the dynamic programming structure that will be needed to store the subproblem results, then the next step is to see how transitions from current state or previous state to current state occur. Okay, transition is like going from one state to another. So the second step is to see the state transitions. Okay, so consider your current state is like this. Okay, so you are at this particular string. So how could you have landed up on this particular string? Okay, so you will consider and consider the previous states that could have resulted into this string. Okay, and you will take minimum contribution from those states, minimum in terms of the minimum number of terms turns needed. Okay, so there might be a possibility that a plus b PAA would have resulted into your current state, okay, this state. And it might have been a possibility that A plus A B A would have resulted into your current state. So there can be states like this, okay. So you essentially want to break the current string into parts and trying to see which of the breaking is giving you the minimum number of turns. So that will be the minimum contribution from the previous state, okay. So you will be wanting to consider the breakpoints in the indices ranging from start index, or let me change the color here, indices ranging from start index till the end index. And breakpoint is just like you are trying to split into a string into that breakpoint, the first section including the start index and the breakpoint, and the rest of the section is including breakpoint index plus 1 to end index, okay. So you can see it on the next page. So then the state transitions will be looking like what, okay. So this is nothing but we are taking minimum contributions from the previous states, okay. So minimum of this much is your previous state. If we talk about the previous states here, so this much is your previous state, and whatever is the current value of your turn index, uh not turn index, actually I have named it index mistaken by mistake, so it should be turns needed, okay. So let me correct that, turns needed, okay. And here also we have to do the correction, okay. I hope you are able to understand. So initially this turns number of turns needed from start index to end index will be set to size of the string, okay. That much number of maximum turns would be required if you are just wanting to print single character at a time, okay. So that's why it's set to size of the string, and then you will be taking minimum of the previous contributions and whatever is the current value of the turns needed, from where to where, start index to the end index, okay. So you will take minimum contributions in this particular one basically. So once you have done all this, then what will be your result? Your result will be that start index is starting at the very first index of the given string and end index is the last index of the given string, okay. That will be storing your result and you will be simply returning that, okay. And that will be your minimum turns needed to of printing to get the string that you want to achieve, okay. So let's see the implementation part, then things will be more clear to you if it is still not clear. So let's take the code to the board. So this is the code for this particular approach, or you can see the implementation of this approach. So here what we have done here is, uh, first of all, as I said, we will be needing the size, okay. It's just a variable that we have used, storing the length of the string that you have to make by printing operations. And this is the dynamic programming structure, DP structure, because two state variables were required, that's why 2D structure is there, okay. Then what you will be doing here is you will be initializing turns needed for printing a single character as one, okay. If you just want to print a single character, if the start index and the end index are basically the same, then you need to just one turn of the printer. So that's why we are initializing that here. Okay, then you have already covered strings of length 1. If you want to print, then you will be starting from the length 2 strings and going up to the entire size of the string. Okay, you can print entire size of the string also by the printer. Okay, this is one of those state variables that we talked about. And from start index to the end index, and as we talked about, we will be using this formula start index plus length minus 1. Okay, to calculate the end index. Okay, so from the start index to the end index, you will be taking the minimum contribution of previous state, and previous state contribution will initially be set to size of the string. Okay, because that will be the maximum number of turns you can take. Okay, so then you will consider the breakpoints. Okay, so these are the breakpoints that we are talking about. So the breakpoints are these. Okay, so like here you are inserting a breakpoint again, this time you are inserting breakpoint here. So these are the breaking indices. Okay, so then uh, you will be using that state transition equation that we talked about. Okay, so from start to the breakpoint index will be one section, and another section will be from breakpoint index to the end index. Okay, that could have resulted into your current state. It's something like this. If a b b, again I am telling you, uh, is given to you, let's say this is your current state. Okay, then one of the previous states could have been that a and b a would have been combined and it resulted into this. Okay, so you are basically seeing how many minimum number of turns needed for this one plus how many number of turns needed for this one. Okay, so that will be your previous state contributions if this particular is the breakpoint. So what we are considering as breakpoint is this much. Okay, so this is the breakpoint. So that's taken care of, and then there might be a special case. Consider this example that this is the given string that you want to achieve. Okay, and these are the indices of that string. So one of the approach can be to, you know, print two a's. Okay, then print single b, then again print the rest of the two a's. Okay, so in total three operations, and you will observe that the character at this particular index 1 and 4 are matching. Okay, so why not do it like this, that you print the entire string up to the whole length consisting of all a's, and then just do a little replacement of b with the by replacing middle a with b, and in this way two operations will be required. So you see, if we are wanting to divide, so this character was matching this character. Okay, so that's why the number of operations or the contribution of previous state was reduced by 1. Okay, from 3 ops you went to 2 ops. So that's why in that kind of scenarios, you can consider your previous state contributions to be reduced by 1. Okay, I hope you are able to understand it. And then you will be simply updating your minimum previous state contribution variable. Okay, so once you have done considering the previous state contributions and have been with your minimum previous state contribution, then you will simply update your current state with that. Okay, and as we talked about, once you are done with all of this uh, procedure, then you will be having the turns needed from the first index. Okay, so this is the first index to the last index of the given string. Okay, and that will be your answer. So this is the whole logic, and this is how you should think when to apply dynamic programming or in a certain problem. And this is how you think about firstly the state variables that will be representing the state. The next step is to think about uh, the dimensions of the dynamic programming structure that would be needed, and the third step is to just see how state transitions will go. It means that going from one state to another, okay, and how your result will be computed. So this is the whole logic and the approach and implementation. If you are still having any kind of doubts or any queries in general, then please feel free to ask them in the comment section. And I really hope this solution walkthrough added some value to your journey of honing your DSA skills. And until next time, keep solving more and more problems. And I will be seeing you in the next video. Thank you for watching.